Hi boys and girls, this is lecture 3.5 in Unit 3. The topic, Implicit Differentiation. What is the difference between an implicit function and an explicit function? Up to this point in the text, most functions have been expressed in explicit form. For example, in the equation y equals 3x squared minus 5, the variable y is explicitly written as a function of x. Notice that y is isolated or solved for. When this is the case, the function is written explicitly in terms of one variable, y. There are terms, however, when you are unable to solve a function explicitly for y. For example, how would you solve the following function for y? X squared minus 2y cubed plus 4y equals 2. No matter how we would try to algebraically manipulate this function, we would be unable to get it explicitly in terms of y. That is when you must use implicit differentiation. Here are some guidelines for implicit differentiation. Differentiate both sides of the equation with respect to x. We're going to go through the equation, differentiating every term with respect to x. Then we'll collect all terms involving dy dx on the left side of the equation and move all other terms to the right side of the equation. Then we'll factor dy dx out of the left side of the equation and then solve for dy dx. This will make more sense once you go through the process once or twice. Let's start with finding dy dx of this equation. Now once again, you'll see that in this situation, you would not be able to explicitly solve for y, but we want to still be able to take a derivative of this function. That's why implicit differentiation is necessary. I'm going to rewrite the function y cubed plus y squared minus 5y minus x squared equals negative 4. Now, as I go through and take the derivative of each term with respect to x, I'm going to attach a differential, either dy dx or dx dx, every time I take a derivative. So for this first term, y cubed, the derivative is 3y squared dy dx, because I took the derivative of a y term with respect to x. For the next term, y squared, the derivative will be 2y dy dx. Again, I took the derivative of a y term with respect to x. Here, negative 5 is the derivative, dy dx, another y term. And then here we're finally at a different variable, an x term, this derivative, negative 2x, and then took a derivative of an x term with respect to x, so the differential that I attach is dx dx. On the right side of the equation, the derivative of negative 4 is 0. Now, as you go through, you'll see that systematically, once again, I took the derivative of each term and attached a differential to each term depending on which variable I was taking a derivative of. A y term with respect to x gets a dy dx attached to it. An x term with respect to x gets a dx dx term attached to it. But these dx dx terms don't really need to be in your final answer. That's really as though it were a 1. So even though I attached that differential for consistency in the process, it's not really necessary. And you might get to the point that when you're taking the derivative of an x term, you don't attach that differential. Now, let's look at step 2. Collect all terms involving dy dx on the left side of the equation and move all other terms to the right side. Well, we only have one term that's not dy dx, so we're going to leave 3y squared dy dx on the left, our 2y dy dx on the left, our negative 5 dy dx on the left, and let's move 2x to the other side of the equation. 2x is the only term on the right side. Step 3 says factor dy dx out of the left side of the equation. Since all of these terms have a dy dx in them, we can factor that out, and that leaves 3y squared plus 2y minus 5, of course on the right side, 2x. To finish off this simplification process, we're going to solve for dy dx by dividing both sides by this factor. So dy dx is going to be 2x over 3y squared plus 2y minus 5. I divided both sides of the equation by this factor. It canceled over here, of course, and left the right side of the equation a rational expression. Now, this is the derivative of this function. Given any point on this rather strange curve, I could take the x and y value, plug it into this derivative function, and find the slope of the curve at that particular point on the line. You can see that with curves like this, since they aren't functions, that we are unable to solve explicitly for y. That's why we have relations like this and why we need implicit differentiation. In this example, we're going to take the derivative of this equation implicitly and use that derivative in order to find the slope of a tangent line at the point, the square root of 2, comma, negative 1 over the square root of 2 on this curve. Rewriting the function, x squared plus 4y squared equals 4. Remember, with implicit differentiation, you go through the equation taking the derivative of each term with respect to x. The derivative of x squared is 2x, and since I've taken the derivative of an x term with respect to x, the differential I would attach would be dx dx. However, I'm going to leave that out since it will not figure in the final function. The second term, 4y squared, the derivative 8y. dy dx, I do have to attach this differential. Anytime I'm taking the derivative of a term with a y, then I must attach the dy dx differential. On the right side, the derivative of 4 is 0. Now remember, step 2 says to move all terms not containing dy dx to the right side of the equation. So that's going to leave on the left side 8y dy dx is equal to negative 2x. Step 3 says to factor dy dx out of all of the terms on the left side. But since I only have one dy dx term, I'll go on to step 4, which says to isolate dy dx by dividing by the factor that you have, which in this case is just 8y. That leaves dy dx equals negative x over 4y, simplifying that fraction. Now this is the slope function for any point on this curve, but we have been asked to find the slope at a specific point. So the derivative at the point, not negative, sorry, let me erase that. Square root of 2, comma, negative 1 over the square root of 2 is going to be negative x, which will be negative square root of 2, over 4 times y, which is negative 1 over square root of 2. Notice in these derivatives we need both the x and y coordinates of the point. Now negative over negative, of course, is positive, so let's simplify this. We're going to have the square root of 2 over 4 over the square root of 2. Since this is a complex fraction, this can become the square root of 2 times the reciprocal of this fraction, square root of 2 over 4. The square root of 2 times the square root of 2 is 2 over 4, which reduces to 1/2. Therefore, the slope of the line tangent to this curve at the point square root of 2 comma negative 1 over square root of 2 is 1/2. Here is another example where we're going to take the derivative of the equation implicitly in order to find the slope at a specific point on our increasingly interesting curves. You can see that the equation is becoming increasingly interesting as well. We're going to need to use a little chain rule, a little product rule, in addition to our implicit differentiation skills in order to take this derivative. First, I'm going to rewrite the equation. 3x squared plus y squared, quantity squared, is equal to 100 xy. On the left side, I have to see this as a composite function, the inner function x squared plus y squared, the outer function a quantity raised to the second power. On the right side, I'll use the product rule to take the derivative of the product xy. So on the left side, the exponent comes around and gets multiplied by this coefficient. I'll have 6 times the quantity x squared plus y squared, and then to the 1 power, because I subtract 1 from the exponent. I don't attach differentials until I start taking derivatives of the individual terms inside, times the derivative of the inner function. The derivative of x squared is 2x, and then since I'm taking a derivative of an x term with respect to x, that differential would be dx dx, which I will not write, plus the derivative of y squared, 2y dy dx. That is the derivative of the left side of the equation. On the right side, we have 100, and I'll leave that outside parentheses and use the product rule on xy. X times the derivative of y, which is just going to be 1 dy dx, plus y times the derivative of x, which is 1 dx dx, not needing to attach that differential. Now I'm going to have to isolate the dy dx terms and move them to the left side of the equation. So there will need to be some distribution here. On the right side of the equation, distributing the 100 gives me 100x dy dx plus 100y. Distributing here allows me to move this term now to the left side of the equation. I am also going to need to distribute this term, the 6 quantity x squared plus y term, to each of these terms. So this becomes now 2x times 6, which is 12x, times the quantity x squared plus y squared, plus, and now 2y times the 6 on the outside becomes 12y times the quantity x squared plus y squared. And then this, of course, has the differential dy dx attached to it. Well, here are my two dy dx terms. They need to be moved to the left side. Any other term gets moved to the right side. So on the left, I'm going to have 12y x squared plus y squared dy dx. I'm also going to subtract over this term, negative 100x dy dx. Those are both dy dx terms. They're now both on the left side of the equation. On the right side, I have the 100y that was already there, and then I'm going to subtract over this term, which means I'll have minus 12x, then the quantity x squared plus y squared. Now it's time to factor out the dy dx. This leaves dy dx. On the left now we have 12y x squared plus y squared minus 100x. Nothing has changed on the right side yet. This is a complicated derivative, isn't it? We're almost done. And now to isolate dy dx, we divide both sides by this term. 12y x squared plus y squared minus 100x, and on this side as well, 12y x squared plus y squared minus 100x. You can see that ends up being the derivative. In fact, I'll just cancel this. Dy dx, cut to the chase, is 100y minus 12x times the quantity x squared plus y squared over 12y times the quantity x squared plus y squared minus 100x. That was really something. Of course, we are asked to find the derivative at a specific point. I think we should change colors. We're going to have now dy dx at the point 3, 1. And as I plug the x and y coordinates into our derivative, we'll have 100 times 1 minus 12 times 3 times 3 squared, 9 plus 1, which is 10. The denominator will be 12 times 1 times, once again, 3 squared plus 1 squared, which is 10. minus 100 times 3. The numerator then becomes 100 100 minus 360, which is negative 260. The denominator, 120 minus 300, which becomes a negative 180. Reducing this fraction, 26 over 18, then we have our slope becoming 13 over 9. That was a lot of work, but with all of the skills at our disposal, the product rule, implicit differentiation, the chain rule, not to mention some simple arithmetic, we arrived at the answer. In this example, we're asked to find the second derivative implicitly. Let's start with finding the first derivative. X squared plus y squared equals 25. The derivative of the first term, 2x, since it's an x term, no need to attach the differential. The derivative of y squared, 2y, and then dy dx. The derivative of the right side, a constant, is going to be 0. Here is our 1 dy dx term. Let's move the other term over to the other side. 2y dy dx is equal to negative 2x. Dividing both sides by 2y gives us our first derivative, dy dx is equal to negative 2x over 2y, which reduces to negative x over y. Now for the second derivative, I'll need to use the quotient rule since the result of my first derivative is a quotient. We're going to have d2y over dx squared is equal to the bottom, which is y, times the derivative of the numerator, which is a negative 1 dx dx, minus the numerator, negative x, times the derivative of the denominator, which is 1 dy dx, all over the denominator squared. This simplifies to negative y plus x dy dx over y squared. Notice the dy dx term that is here in our second derivative. We're going to replace that dy dx with the result we found in the first derivative, negative x over y, which means our second derivative will look like this. We'll have negative y plus x times negative x over y squared, which becomes negative y minus x squared over y squared. And to simplify this complex fraction, I'm going to multiply the numerator and denominator by y, which will give me second derivative of y with respect to x is now equal to negative y squared minus x squared over y cubed. Now this is the second derivative, and if we were plugging in a specific point in order to get a slope, we could do that here. But let's notice something. If I factor out a negative 1, this leaves x squared plus y squared in the numerator over y cubed. And remember our original function, x squared plus y squared equals 25. Therefore, we can replace this x squared plus y squared in our second derivative with 25, leaving a simplified second derivative of negative 25 over y cubed. In our last example, we're going to find the equation of a tangent line to a graph. Of course, we'll need two things, a point, which we are given, and a slope, which we will find by taking the derivative of this equation implicitly and then using the point we are given. First, I'm going to distribute this x squared to make this equation a bit simpler. This will become x to the fourth plus x squared y squared equals y squared. When taking this derivative implicitly, I need to remember to use the product rule for this term. The derivative of the first term, 4x cubed, since it's the derivative of an x term, no need to attach the differential. And using the product rule, I'll have the first term times the derivative of the second, x squared times the derivative of y squared, which is 2y dy dx, plus the second term, y squared times the derivative of the first, which is 2x. Again, another x term which does not require a differential. On the right side, the derivative is 2y dy dx. Now let's collect the dy dx terms to the left side of the equation. This will be 2x squared y dy dx, and I'll subtract over the 2y dy dx. I have two terms that do not contain dy dx, and they need to be moved to the other side of the equation. That will be a negative 4x cubed minus 2xy squared. Let's factor out the dy dx. This leaves 2x squared y minus 2y equals negative 4x cubed minus 2xy squared. And for our last step, we'll divide by this factor, creating our derivative. Dy dx is equal to, since these factors cancel, negative 4x cubed minus 2xy squared over 2x squared y minus 2y. Since all of these terms can be divided by 2, let's simplify this a bit. Negative 2x cubed minus xy squared over x squared y minus y. First derivative. Of course, this will find the slope at any point on this curve, but let's find the slope at the point we're given, square root of 2 over 2, comma, square root of 2 over 2. Dy dx at the point square root of 2 over 2, comma, square root of 2 over 2 will be negative 2 times the quantity square root of 2 over 2 cubed minus the square root of 2 over 2 times the quantity square root of 2 over 2 squared. That's your numerator. In the denominator, the square root of 2 over 2 squared times the square root of 2 over 2 minus the square root of 2 over 2. In simplifying the numerator, when we cube the square root of 2, we get 2 square root of 2. Multiplying that by the negative 2 gives us, we'll just move this down here now, a negative 4 square root of 2, but cubing the denominator gives us 8. So that's simplifying this first term. In this second term, we again are cubing the square root of 2, which will give us a 2 square root of 2 over, again, 2 cubed, which is 8. So this will be minus 2 square root of 2 over 8. For the denominator, we are once again cubing the square root of 2 over 2, which will give us a 2 square root of 2 over 8 minus the square root of 2 over 2. Now I'm going to change this denominator so that it has the same denominator as the first fraction, which will be 8, by multiplying by 4 over 4. So that denominator will become, just looking at the denominator, 2 square root of 2 over 8 minus a 4 square root of 2 over 8. Now we're going to have in the numerator, and the same numerator. Simplifying this gives me a negative 6 square root of 2 over 8 over, since this is now a 2 minus 4, a negative 2 square root of 2 over 8. Now if we can think of this as a negative 6 multiplied by square root of 2 over 8, a negative 2 multiplied by a square root of 2 over 8, this simplifies to 3. Believe it or not, that is the slope of the tangent line at the point square root of 2 over 2, comma, square root of 2 over 2. Now let's write our equation of the line. Y minus the square root of 2 over 2 is equal to 3 times x minus the square root of 2 over 2. This becomes y minus the square root of 2 over 2 equals 3x minus 3 square root of 2 over 2. And when we add that square root of 2 over, we're going to have y equals 3x is minus 2 square root of 2 over 2, and that becomes, of course, just square root of 2. So our final equation, 3x minus the square root of 2. And that is your answer. That's it for today's lecture. This illustrates the need for being explicit when showing your work. God bless you, boys and girls.